Two of the most important waves we study are sound and light. So let's start talking about those two waves, and we'll begin with sound. And we'll ask, how is sound a wave? How does it work? Well, let's start with how a speaker works. To get an idea, pick up your cell phone, turn on some music really loud, and lay your hands on top of the cell phone. What do you feel? Chances are good you feel vibrations, and you feel the vibrations coming from where the speakers are. So when the speaker vibrates, that's what produces a sound wave. If that's enough information for you, you can skip ahead a couple of minutes. If you'd like to learn a little bit more, you can watch this video.
Hi, I'm Marshall Brain.
And I'm Tom Harris.
We're here to describe how a speaker works today by showing you a very simple experiment you can do with the base speaker out of any speaker enclosure you might have. Tom has a 9-volt battery and I have a speaker. Let's go to a close-up and show you how this works. Any speaker has two contacts on it. It's a very simple device. The two wires go to the electromagnet inside the speaker coil there. So if you attach a 9-volt battery to it, as Tom will demonstrate here, the speaker will respond, and it will respond quite aggressively if it's a big bass speaker like this. So let's rotate it so you can see one other view of this. And you can see this speaker really responds. So when a speaker is inside the stereo, you're just pulsing it with a power signal, a voltage, just like that 9-volt battery, that's making that speaker move up and down much more rapidly in the case of music, maybe 40 times a second or 50 times a second, something like that for the bass speaker, but it's that exact same process. So that should help you see how simple the speaker is and how it actually works in a device.
So we see that sound waves are generated when the diaphragm of a speaker moves back and forth, and we're going to look at that a little bit more. So if you have a speaker and you pop the top off of it and you play some music, you can definitely see it moving back and forth. This is from the Big Bang Theory.
Okay, we're all set. Let her rip. Hey, check it out. It's just cornstarch and water.
They make up a non-Newtonian fluid, which is liquid, but solid under the percussive action of the speaker.
That's what makes it.
Okay, so that's absolutely true. That works. We do this all the time when we do science outreach, especially with the younger kids. You can absolutely try this at home, but I would recommend you cover up your speaker with a big garbage bag first so you don't get the cornstarch down into it. So the next thing we're going to look at is, how does that vibration of a speaker, the diaphragm of a speaker, how does that make a sound wave? So to start, let's remember that a sound wave travels through air. Air is the medium through which the sound wave travels, and in particular, the air molecules. A sound wave is comprised of vibrating air molecules, and we're going to look at that part next. So let's think of the impact of the motion of the speaker on the sound wave. This is another PhET simulation. If you Google PhET, P-H-E-T, sound wave, you can get to this guy. In this simulation, we see all of the air molecules. Some of them are colored red, just so we can see that although they will vibrate, they don't really translate very far. When I play the video, I'll click the speaker and make it make a sound, and we'll watch what happens to the molecules. Okay, first I'll just make a single sound. See, some of the molecules got bunched together, and then that bunch kind of spreads. We can also make a continuous sound. So what we see is that when we make the sound, first the speaker bulges forward to the right in the video. When it bulges out, it makes the closest air molecules squish together, it compresses them. Then the speaker retracts and it moves back towards the left, and then those air molecules spread out. But the molecules that were bunched up together, they bang into their neighbors. So that compression, that area of close molecules, that travels. So they push into their neighbors, makes them compress. Those neighbors push into the next neighbors and they compress, and then that travels out. The regions where the air molecules are close together, those are called compressions, and the regions where they're spread out are called rarefactions. And those changes in the air, those variations, are the sound waves. So just play it once more. So we see that the compression travels out as well as the rarefaction behind it. And then the continuous wave does the same thing with multiple compressions and rarefactions. And then overall, once the wave is passed, those red molecules, they go back to their original place. So overall, those air molecules haven't gone anywhere, even though the wave did travel. What we could see in the simulation on the previous slide is that the nature of the traveling of those air molecules, the vibration of the molecules, was very much like the longitudinal wave on the slinky. So it turns out that sound waves are longitudinal waves in air. They travel by means of compressing together and then spreading apart. And we're going to show that with air molecules on the next slide. So for comparison here, we have a picture of the slinky with the wave, the longitudinal wave on top, and we have the picture of the loudspeaker with air molecules in the middle of the slide. Just like the slinky has places where the elements of the medium, the coils, are close together, the picture with the speaker has areas where the molecules are close together. Where they're close together, that's called a compression. That's a place where the air pressure is high relative to equilibrium. And in our slinky picture, we have places where the coils are spread out. That's a rarefaction. In our air wave, we have rarefactions where the air molecules are spread out. In those regions, the air pressure is low compared to equilibrium air pressure. So our sound wave is a pressure wave in air. So it's a wave or a variation in air pressure. In our picture of the sound wave here, now this has been greatly exaggerated. Of course, air molecules aren't that far apart, but it does help us look at it. What do we need to finish up with here? How does this air wave become sound, something that we hear? Well, those compressions and rarefactions, they just travel along the air until they hit an eardrum. When they hit an eardrum, they make the eardrum vibrate back and forth, and your brain turns that vibration into sound, into something we hear. So that tells me that biology is actually pretty cool, even though I was always terrible at it, but biology is neat. Then I think the last thing we'll say is that sound waves are sinusoidal waves, so all of the treatment we've done until now about sinusoidal waves will apply to sound waves. Sound waves are sinusoidal waves because the source, for example, a loudspeaker, moves with simple harmonic motion, just our previous spots. So now the next thing we'll discuss will be the speed of sound as it moves through a medium. The speed of a sound wave depends on how the compressions can travel through the medium. In air, the travel depends primarily on temperature. It also depends on humidity, but temperature is the big one. The temperature dependence is given on the slide. It's not a perfect way to calculate the speed, but it's not bad. It gets pretty close. In our equation, T stands for the temperature of the environment. It's in degrees Celsius. If we're at room temperature, then the speed of sound is 343 meters per second. When we come across problems, if you're given the air temperature, then you're expected to use this equation to solve for the speed of sound. If you're just given a problem where there's sound in air, it doesn't say anything about temperature, then you can assume it's at room temperature and you can use 343. So now, ears, human ears, animals of course are all different. Human ears can detect sound waves with frequency between about 20 hertz on the lower end and 20 kilohertz or 20,000 hertz on the upper end. The lower frequency sounds are perceived as low pitch or bass notes, and high frequencies are heard as high pitch or trebles note. An activity that I would do in class, and I'm going to suggest you do at home, would be to open up an online tone generator. I've got one address on the slide here that I use, which is pretty good, and test the limits of the range of your hearing. What's the lowest frequency you can hear, and what's the highest frequency you can hear? For me, I can hear down to 20 hertz, but in the upper range, it completely cuts out. I lose it at about 16,000, 15,000, and it's just because I'm old, actually. As you get into your 40s, you lose those upper frequencies. So young people in general can hear up into the 20,000, even a bit higher. And then when you get to be my age, you don't hear it quite as high. When I was doing this with my dog in the room, he went a little bit bananas at those high frequencies. So clearly he could hear them real well. So I'm going to suggest you try that out, and then pop over to the discussion groups and share your results and see how other people did as well. We normally think about sound traveling in air, but it also travels in other media. I'm going to just play a quick video first, and then we'll discuss the other kinds of media.
Their pace is quickened. They must have caught our scent.
Hurry! Come on, Ghibli!
Okay, that's from Lord of the Rings, of course. So what happens is that the orcs captured Merry and Pippin, and Strider is trying to catch them with his friends. They're far away, so Strider puts his ear down to the rock and listens, and he can hear the vibrations through the rock that tell him where the orcs are. It, of course, is very exaggerated in the movie, but it is a real phenomenon. You can hear sound travel through solids. So my first suggested activity is that if you're fortunate enough to live with somebody else, grab a friend or a family member and get as far apart as you can, either in a room or a hallway. Have one person knock on the end of the floor and the other person listen. Can you hear the sound travel through the floor? The other thing I would suggest you try is something maybe you did as kids, maybe not. Grab 2 metal cans, 2 empty tomato sauce cans or whatever, punch holes in the bottom and string a string through it. Make phones out of the 2 tin cans and a string. One person talks into one can, the other person listens at the other can. How far apart can you be and still hear the sound, still understand? This totally works. My brother and I used to do it when we were kids all the time. And I've done it in class before. So give it a try. Again, pop over to the discussion groups and compare with what other people have. You can also hear sounds through liquids too. If you've ever been swimming, of course, you can still hear things when you're underwater. Then one last example, sound waves with frequencies above 20 kilohertz. They're called ultrasonic, and we use those in medicine. So we send those ultrasonic waves through the body, let them bounce off something inside a body. The picture we have here is a baby. That's kind of a typical use of ultrasound. The sound bounces off and that echo is recorded. You can form an image using that echo of what's inside the body. Taking pictures of babies before they're born is the typical one, but it's a really important diagnostic for kidneys, heart health, all sorts of things that happen. So next we'll talk about light waves a little bit. We know that light waves move through a vacuum, therefore light waves don't require a medium, but it is definitely still a wave. So you got to ask the question, what is waving? Turns out it's the electric and magnetic fields that are waving. We're going to come back to those and do more later. And it was a really hot topic of study and theory in the 1800s when they could create EM waves and they could also investigate them. So one thing we know about light waves is that it's an electromagnetic wave, and all electromagnetic waves travel with a constant speed. The speed in a vacuum is given by c, and c is 3 times 10 to the 8 meters per second. 10 to the 8 meters per second. So that's the speed in a vacuum. Of course, that's very fast. So hard to write on a trackpad, sorry. Takes about 8 seconds for light to get to us from the sun, so it does travel really, really fast. So that's the speed of light in a vacuum. Electromagnetic waves do have lots and lots of different frequencies and wavelengths. We see a small range of them in the visible light spectrum between 700 nanometers and 400 nanometers for the wavelength. But of course, there's so many more. For AM radio, that's got frequencies of about 10 to the 6 hertz. That's kind of radio and TV is getting in that range, 10 to the 6, 10 to the 8 hertz. The infrared spectrum, sorry, I just dropped my mic. The infrared spectrum is kind of interesting. That's where we have night vision goggles, so that's kind of cool. Then up at the upper end, 10 to the 18 hertz or so, that's where we get x-rays, a lot of medical applications. So the whole spectrum we kind of experience in our lives, even though we don't see everything.